Oh, not as much.
Hi, my name is Kyle Phillips. I'm a verification engineer at IBM, and today I'll be talking about the event framework, which is an open source header-only C++ event system that we use for hardware verification. Okay, so what is an event? Event is just basically a unit of activity that we can structure verification around. So think about if we do an instruction fetch 2 cycles ago and that's being decoded this cycle, we want to check that that happens. We can think of the instruction fetch as an event and the decode as an event. So I'm going to talk a little bit about what makes this a little different than other event systems that are out there and why it's useful for verification. So basically this is really just like an event callback system. You post the event, you get the callback. So here you can see how it works. It's post the event to event framework. It goes through a filter and then it gets into a handler function. Okay, so handler functions are just basically any sort of function that accepts that event type as an argument. They don't know anything about the posters, they just get called automatically. So we also have this thing called filter functions, which are just predicates for calling your handler. They just return true or false. They can determine when the handler is called. So you register with them with your handler. So what's interesting about this is we also have this thing with event histories. So we can define a clock for each of our events, which are also just another type of event. And so when we post the event, we can then post the clock event and have it moved into the next stage. And we can also have delayed handlers, right? So we can have the event get to 2 stages later and then get the callback. So we have this, it's very useful. And we also, if you hate callbacks, you never want to use them, we also have the ability to query the history of all the events posted, and you can use that for your verification. So if you want to do histories, hopefully you can
Hi, I'm Gurtej Randhawa, and with me today is Nicholas West and Rowan Talbot. We're from Schulich on a Chip at the University of Calgary, and we just finished our first year. So, reflecting on our first year as a club as Schulich on a Chip, here are some of the issues we've noticed. People just don't know what chip design is. Like, if we're telling someone else that we're on a chip design team, or our parents are telling their coworkers, sometimes we get a funny look, and they'll ask genuinely, potato chips? So that's that. And then another thing is that people who are motivated to learn struggle to pick and choose between the vast amount of resources that there are. So it's just overwhelming at the start for the average person.
Yeah, so what we're going to do looking forward for our club in like next year, next 5 years, is kind of try to make media. Like a lot of our members learn through YouTube, social media, like and all that jazz. So we want to be kind of that middle that we feel is missing of taking the resources that are there and that we know exist and kind of pipelining them and making them more accessible and like free and for a wider audience. And
yeah, so the goal is just to bring stuff we've learned at this conference, such as the 0 to ASIC stuff, and just give it to people that are very willing to learn, but just don't know how to get started. Also, if we could, like, both today and tomorrow, see what you guys think is the best way to get started, and things you wish you had in the program, and the time. Silence.
Oh boy. ASIC jokes. Oh, that's terrible.
Hello everyone, my name is Omar. I'm the UW ASIC Analog Team Lead. So I'm going to present really fast because this is a 4-minute presentation, now we have 2 minutes. Okay, so what's the problem with analog design now? Is that we have a few long steps, but the last 2 steps are optimization problems. So let's look into those. That's what I'm working on right now. Ooh, I skipped 2. Ooh. Am I good? No. Okay. Looking at setting. So we're gonna learn from GM over ID. We notice that W is mostly linear, L isn't linear. So now, if I want to make an optimizer, it's gonna be big O of L time instead of big O of WL. Okay, so I'm like, okay, let me make an optimizer. But for that, I need a special spice simulator. So I was thinking, okay, what if I make an incremental spice simulator? And those are the cache stages. So the two hop neighbors is you only look, you only calculate the two neighbors relative to the device change. I'm going to skip all the caches. This is a full flow. It's made modular in Rust, so people could add their analysis techniques. Everything's exposed for you. Okay, this is the ink spice, or incremental spice. Now let's look at layouts. So I want to automate layout, like a bunch of people did today. And there's two different routes that I can take, proprietary or open source tools. Open source tools have align and magical. I'm going more down the deterministic route when they go down the ML route. Okay, so this is what I do. So first of all, I have the constraint detection, and there's a few constraints: symmetry, matching, proximity, isolation. And this scans in big O and squared. Next, I have simulated annealing for placements. And you can see here, there's a reward function, there's a class function, there's everything like that. Now there's routing, multi-layer A-star, and there's a few steps here, and I have my own incremental DRC text and LPS. Okay, this is a full flow in progress. We're testing the satisfaction.
Hello everybody, my name is Arthur. This is Archie. I'm going to be presenting a cryptography hardware simulator today. We're here to represent the RQ Hard Design Club, which was founded in November 2005, so it's a new club. And I'm focused on bridging academia and industry through open source projects. And the motivation of our projects are IoT security, which has quite a few challenges, but the ones that we're focusing on are traditional encryption, computer intensive, very large heavy, and low power devices lack the hour and power budget for those kind of projects. We had to choose a cryptographic standard that was efficient operating design with simple and fast operations, and it was lightweight, cryptography. We ended up choosing this SB122, which in November of last year was selected as one of the cryptographic standards, and it's a lightweight design for low memory and footprint and high efficiency.
Alright, so I'm going to talk about a bit of our design. So this is the ASCOM core. It uses a sponge construction, and it has parallelized 560 word with the bits word, so it's the entire 320-bit state, and it permutates through 3 different layers. So the constant addition layer injects a specific constant to add more uniqueness. The substitution layer mixes it around to in a specific way to add more nonlinearity. And also the diffusion mixes all of that information around throughout the state to make it, again, nonlinear. And this is our top architecture. So you can see our data path as well. So we have the ASCON controller, which feeds into the core. The controller has the AEAD, which is the authentic encryption with associated data, and also the lightweight hashing algorithm. We also went through with the full RTL to GDS2 flow, and we got, these are all the metrics: 100% close timing, clean DRC, and clean LBS physical sign-off. For the future of the roadmap, we're adding more optimization that won't target async computation and the for an entire spot that is contributing to your open source projects and future plans and events. Thank you.
This is your phone? Hey, your phone?
Did someone pay both guns?
Oh, that's fine. Sorry. Anyway.
We'll get it later.
Well done, guys.
Good.
No
All right,
pressure.
yes. Okay, 18 things that I have done to Magic in the last year, or as many as I can get through before the time's out and somebody drags me off the stage. So first, I put in a new archive command. It's similar to backup. You can put an entire design, make a snapshot, and put it into a single file. I created a units command. There used to be a snap command, which was affecting units, and that was a stupid way to do it. So I now have units. Units just controls units. Units microns, units internal, units lambda. More support for CDL format. Nobody knows really what CDL format is, or it's either proprietary. So I have some support for some things in CDL. There is a connect and disconnect in the extraction deck, so you can make separate extraction decks for soft connect errors and so forth. The tool command setup used to be hardwired, so now I have the tool command set up so that you can do macro rebindings for both buttons and keys for each of the tools. I got the DRC into a state a few years ago where it just says see error in subcell, and you have to keep going down to the subcell to see what the actual DRC error is. I finally figured out how to get rid of that. A really useful thing, GDS output operators interacting, overlapping, and tagged. These are things that most DRC engines have that Magic previously didn't. Likewise, for input operators, there's a not square that's good for bar contacts. There's another one called tagged, and this is for labeling layer, so that you can do something special with it. The RC extraction in Magic was a big mess, and I have pared that down. Extract do unique is better than extract unique. I got rid of the whole sim file format thing. And the extract resistance extraction can just be an option extract to resistance. The parallel processing enablement allows people to map command lines to request to property rights.
Hi, my name is Wadud Wase. I interned last summer with Dr. Tim Edwards, and we worked on the Vectrus V core. So Vectrus, the thing that was wrong with it was that its performance was 200 times slower than expected, even though it was supposed to be an upgrade to the Pico RV32. And we believe the reason was the 16-word instruction cache, which was severely limited, causing constant cache misses. So we decided to research how cache sizing affects it. As for hardware, we use the A7100P from Xilinx Artix. We use the min debug cache variant that has an RB32i instruction set. And there was variable memory, and we used Vivado. As for cache configuration, started from 16, went all the way up to 8192 words, which is about 32 kilobytes geometric progression times 2. We use Drystone 2.1. And for performance metrics, we measured all the standard metrics, block RAM utilization, and bloods. As for performance improvements, this was supposed to be a 3-minute talk, so we're going to have to skip over a lot of these graphs, but exponential until there, where the entirety of the Drystone benchmarks just gets loaded into cache, so no more performance improvements past that. Same for the DMIPS, which got an 84 times improvement. As for the performance, there was about 3 regimes, one where there was just severe cache crashing and about nothing improved, or not by much. Regime 2, which was from 512 to 1024, in which performance actually jumped significantly, and then diminishing returns after that because everything got loaded, the entire cache got loaded into the cache. As for the block RAM utilization, looking at it, we determined that the 1024 words were the best options because they didn't get that much block RAM compared to the others. And with the people who are components, thank you.
All right. Hi, I'm Matthew Balance, and I'm here to talk about how to manage your verification coverage data. More and more of our open source design tools are actually producing coverage data. Verilator, CocoaDB, AVL, each have their own coverage data formats, and we really want to be able to see that data in one place. The good news is that there is an industry standard for the data model and API for dealing with coverage data. The better news is that there's an open source library that implements that API and provides a database and tools for working with that. So at the end of the day, you have a kind of a one-stop shop for dealing with your coverage data. Over the past year, or frankly the last 6 months, there have been quite a few changes in terms of the types of input formats that are supported. Much longer list here of coverage data that we can bring in. We also have new output formats and storage formats, including a custom binary database that is actually quite performance and space competitive. As well, there are some new AI-friendly commands for querying data and getting insights out of the coverage data that you have collected. One thing that I'll just show in screenshots is there is a new text-based way, console-based way of navigating and looking at your coverage, which keeps you in the terminal. You don't have to launch a browser to take a look at your coverage. There are quite a few more screenshots here, but you'll have to do that, look at that on your own. And there is a pretty strong roadmap here in terms of bringing in extra data formats and supporting new ways of visualizing the coverage that you have. Thank you very much.
Okay, so system Verilog. We can read the spec together. This is section 4.3. The system Verilog language is defined in terms of a discrete event execution model. So far, so good. Within the following event execution model definition, there is a great deal of choice. And differences in some details of execution are to be expected between different simulators. This also implies synthesis tools. So that's maybe not that great. Let's talk about the deassign keyword. How many of you know what the deassign keyword is? That's all the people I thought about. Okay, so apparently you can assign inside an always block like this. So if con happens, X will become Y and be connected together. So even if con isn't true anymore, X will still have the value of Y when Y changes in the future. Of course, you want to undo this at some point. You might want to go back to having Z there. So then you can do deassign X. I don't know why you would want to do this. We are not sure what value X will have if Z doesn't change, but you know. The Verilog standard says that you can use this to implement a D flip-flop, which is a lot longer than a normal D flip-flop. Also, this should be a non-blocking assignment, not a blocking assignment. This does not work as a flip-flop, because it's a Verilog. This is verbatim in the spec, in the latest version I checked. Also, this is deprecated to be deprecated, so the procedural deassigned constructs are under consideration for deprecation. Thank you very much.
I've never heard of DSM. That's amazing.
Okay, so this is an FPGA board. How do we know it works? Well, we blink a light on it, of course. And so I think that everyone should blink lights on their FPGA board. So I created a project Led to Believe, which is supposed to contain blink examples for every FPGA board in existence. Currently we have 129 boards supported, and I want to have many more, of course. So how do you add your own board? Do you use ViewSox? Do you just add to your code description file, you just add, for example, which file, constraint file that you need and some extra information, and then you run ViewSox and you will get blinking. Okay, so now we covered part 1 here. Let's move to part 2 and implement RISC-V CPU instead. So by accident I also created the world's smallest RISC-V CPU, the award-winning SERP. I don't go into detail, but it's big serial, that's very small. It's like 125 LUTs on an AMD RTX 7. You can compare it to other processors. It's slightly larger than the Intel 404, it's slightly smaller than the Intel 808. Okay, so now we can just do the same thing here, you know the drill by now. Just add like clock iteration and a constraint file and create a target for it. And then we can run like this. And we have support for our new board. Now, of course, we want to see how many owls we can draw on the same paper, or rather, how many RISC-V cores we can fit into one FPGA, and that is project's core score. So what it does is that it takes a lot of serve cores and prints a message, and we put them into a gigantic mux, which is terrible for routing. And then we can see, for example, we have 10,000 RISC-V cores on a larger FPGA here. And the same thing applies here, just add your new target, and you can see you have a core counter 268 for this one. And you can do the same thing, and I'm done. Thank you.
Hello everyone, I'm Connor. I'm an undergrad at UC Berkeley and I'm presenting Rivet. So many existing physical design flow managers are like trying to abstract away the minimum typical rating that happens in physical design. And this abstraction can be sometimes sort of leaky because most tape-out flows still require custom tickle to be written for industry processes in TSMC. So to get away from to minimize the complexity, we want something that's simple. So here's Rivet. So Rivet is a bare bones signal templating system with parametric flows, full control of flow execution, sharing checkpoints between users, and strong typing for improved autocomplete and compiler errors. So Rivet uses a DAG of steps for a block level flow, and these will be strongly typed to be tool-specific steps like a genus step or invis step. And each of these has a parametric list of substeps, which are generated by Rust functions that have our tickle strings. And we can pin substeps or steps to skip execution, and these can be shared databases that are generated from genus or invis. And in this tool, we organize plugins via Rust crates. So there's a tool plugin crate, a PDK plugin crate, and a flow plugin crate. And we can generate hierarchical flows from this by having an input of a hierarchy and then mapping it to block level flows for each block in the hierarchy. And so here's an example for Rocket Ship. So I create a repo that uses Rivet and it generates a flow using cargo test that I wrote. And it utilizes the reference flow from our Scala 30 cadence plugin. And this is, in the repo we define the floor plan of flow configuration in Rust. So the Rivet generates a tickle, executes a Scala 30 restaurant generator SRM22, and invokes cadence tools. There's a QR code for the repo, and this is the GDS of the farm. And then the conclusion is that Rivet is an open source simplified accessible design flow manager with clear APIs via the Rust type system, and enables quick iteration of system design code for
And that was all. Thank you, everyone.